This is the video for section 10.4 on area and arc length in polar coordinates. So, just like we saw in the previous section, once you have a notion of polar coordinates, you can start to do calculus in that system. And so let me remind you that polar coordinates have to do with x equals r cosine theta, y equals r sine theta, and we're looking at graphs of polar curves which have the form r equals f of theta, so some function of theta. Now what we're interested in doing is understanding how one understands area and arc length in this context. So the basic picture for area looks like this. So you have some region r equals f of theta in a range of theta values like this. Graphically speaking, that says that you're looking at a range of theta values from alpha to beta, and you've got some starting point for your curve and some ending point for your curve, and your graph of your curve maybe looks something like that. So that's your r equals f of theta, and the area that you're computing in that case is this little wedge-shaped region here. And the formula for that area is an easy one, so it's the integral from alpha to beta of 1/2 f of theta squared d theta. And since r equals f of theta, we frequently rewrite this as the integral from alpha to beta of 1/2 r squared d theta. Okay? And this formula is easy enough. I'm not going to do an example here. You can look at example 1 in the book. And you can look, the book gives an explanation for the derivation of this formula. Let me just give you a hint about how that goes. So it's based on taking this region that we have and slicing it up according to a variety of theta values. And then when you go down into the Riemann sum, the integral, so what you do is you take a sector of a circle of radius r, so that's r here, and I have, so the sector is the pi, the slice of pi that you get by slicing out an angle of theta, and the area for that sector is, where's my formula? There it is, 1/2 r squared theta. Notice that there's no pi number in there. Okay. Now, in more interesting area examples, just like in regular XY calculus, we had the area beneath the curve, and then we looked at area between curves. We can do the same thing here. So if you have two curves, let's say you have something like a rose, like what occurred in one of the examples in the book. And then maybe you have some circle. So both of these perfectly reasonable curves, and maybe you're asked to find the area that is outside one of the curves but inside the other curve. Or maybe you're asked to find the area that's inside both the curves. Okay? And so one can do that in the polar situation by computing the area that you want in terms of the, say, the area, you could take a big area minus a small area using the formula that we had up here and taking the difference between those. Okay, for instance, that's how you would find the red area by computing the full volume of this petal of the rose and then subtracting from that the area inside the other piece. Okay? Now let me give you an example of one of the other sorts on the next page. So, for example, if I ask you to find the area inside both of the following curves, so r equals 1 plus cosine theta and r equals 1 minus cosine theta. Now if you go through, the first thing that you should always do in a case like this, because polar coordinates are relatively new to us, is to create a graph. So I want to graph those curves. And so I'll do that with a table of values in order to get a sketch going. So theta values, I'm interested in what happens with cosine of theta, either with a plus or a minus. And so we'll have 1 plus cos theta and 1 minus cos theta. And the relevant theta values are going to be 0, pi over 2, pi, 3 pi over 2, and then pi will just, 2 pi will cycle us back to where we started. Cosine values are 1, 0, minus 1, 0, and 1. When I add 1, we get 2, 1, 0, 1, 2. And when I subtract, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1, 2, 1, 0. There we go. And so if I plot those curves on the same coordinate system, so remember these are these two columns are giving my r values for the two curves. And so for instance, when theta equals 0, my first curve has r equals 2, so I have this point here. And when it moves to theta equals pi over 2, I have r equals 1, which is occurring here. And I have a nice smooth transition between those two because cosine, as I move through that range of theta values, goes nice and smoothly from 1 to 0. And then my next point with theta equals pi, I'm going to have radius equals 0, and then like so. Boom. This. And this shape is what's called a cardioid. Cardioid. Cardioid as in cardiovascular, as in having to do with the heart, because it is heart-shaped. There we go. And the second curve you can plot similarly, although it has a different, so it starts here at the origin, it cycles out like that, and then it comes over to the extreme point back here, and then comes back around like this. And for the blue curve, this is theta equals pi over 2 for both curves actually, and this intersection point is theta equals pi 3 pi over 2 in both of the curves, which is nice. It means that we have identified sort of relevant intersection points for the two curves. They also intersect at the origin, and we'll talk about that in a minute. Now the area that I'm trying to find is the area that's inside both the curves. And so that's this red region here. And by symmetry, what we'll do is we will, in fact, compute. I'm going to look at one of these pieces, this one here, and we'll call that very solidly shaded region A. So sorry, let's not call that A, because A is going to be the full area that I care about. So the area of the shaded region like this is going to be equal 4 times the area of the really darkly shaded region like this. And so I need to compute that very darkly shaded region there. And notice that that is determined by the blue curve. So the blue curve, you'll remember, is this one. And it's determined in the range of theta values from 0 to pi over 2. And so we have that the area is, so we have times 4, the integral from 0 to pi over 2 of 1/2 r squared d theta, using our area formula that we had a minute ago. And the r squared formula that we use here, so I'll combine the 4 and the 1/2 to give me a 2 outside, integral from 0 to pi over 2, using this 1 minus cosine theta squared d theta. And if you go through and do your thing, evaluating that integral, so we 2 integral 0 to pi over 2, 1 minus 2 cosine theta plus cosine squared theta d theta. And then you rewrite cosine squared using our trig identity. So we have 2 times the integral from 0 to pi over 2 of 1 minus cosine theta plus 1/2 1 plus cosine 2 theta, and then with a d theta there at the end. And that's something that we can integrate pretty easily. Let me not write out all the details for that. The answer that I came up with is 3 pi over 2 minus 4. Something to be careful about in examples like this is you'll want to be able to, so in that last example, we were able to find the intersection points of the two curves really easily. In general, though, you won't be so lucky and you'll need to use some algebra or some trig to find the intersection points. And you do that, so in the general case, you would take your f of theta curve and set it equal to your g of theta function. So in our situation, you have 1 plus cosine theta equals 1 minus cosine theta. And when you simplify that, we get 2 cosine theta equals 0, cos theta equals 0. So that happens when theta is pi over 2 and 3 pi over 2. Just like we found in the example that we were looking at. Remember that those looked like this. There's the pi over 2 intersection point, and there's the 3 pi over 2 intersection point. Notice, though, that this technique, and we have to be very careful in general with finding intersection points, this technique misses the fact that the point of the origin can be found. And the reason is that in the first curve, you're representing the origin as, so you can represent this in polar coordinates as radius 0 and angle equals pi. But in the second curve, it's being represented as radius 0 and angle 0. Okay. And so the fact that we were using thetas in order to find the intersection points, because they don't have the same theta value, means that we couldn't find that point. And so the key thing to remember here when you're doing one of these problems is to always make sure and sketch your curves to make sure that you're finding all of the intersection points that you think that you should be finding. Okay. The other thing that can happen is that you can have points on curves that are represented by negative r values, and so you might also have to consider looking at things like f of theta equals minus g of theta. Okay, so again, good idea to always sketch out your curves when you're doing one of these area problems. Okay, last topic is arc length. And the general formula here, as always, we're looking at the integral from alpha to beta of some form of ds. And the ds formulation that we have in polar coordinates is the square root of r squared plus dr d theta squared times d theta, or if you like, in terms of f, the square root of f of theta squared plus f prime of theta squared d theta. So this looks similar to previous versions of ds that we had, right? It was always the square root of something squared plus something else squared. This one looks a little bit different because I have r's and dr's, or f's and f primes. And this is one that you're just going to want to remember unless you feel like looking it up in the book and understanding where the formula comes from. Okay? And I will try and do an example of one of these when we meet in class instead of doing it here in the video. So therein is the end of the lecture on section 10.4.